can't hear the voice.
Yes, we can hear it. Please let it run. I don't think we have time to run it to the end, but just let it run now.
Okay, I will. Maybe I can adjust the speed.
Hello everyone, I'm Sun Bing. Today I'm going to present our work, Probabilistic Verification of Neural Networks Against Group Fairness. This is the outline of my presentation today. I will start with introduction and motivation, followed by our problem, approach, and experimental results. Lastly, I will talk about our conclusion. In recent years, neural network-based machine learning has found its way into various aspects of people's daily life, including fraud detection, facial recognition, self-driving, and medical diagnosis. Since neural networks are used to make critical decisions in a wide range of applications, their dependability becomes crucial to us. Among all desirable properties, such as robustness, transparency, privacy, and so on, fairness is the one that brings much attention, which has societal impacts. Trained neural networks could be discriminative or unfair. Models that suffer fairness make different decisions for different individuals or subgroups, which results in individual discrimination and group discrimination. These subgroups or subpopulations are often determined by different values of protected features like gender, age, and race. And recently, there have been multiple attempts on analyzing and improving fairness of neural networks with a focus on fairness testing, fairness training, and fairness verification. Here, our focus is fairness verification, where we aim to verify fairness property against neural networks. In this work, we investigate the problem of verifying neural network against independence-based fairness. Firstly, we define this fairness here. A neural network N satisfies independence-based fairness if the protected feature F is independent to the prediction Y, which is shown in equation 1. Let us take the network trained on the census income dataset as an example. This dataset is used to predict whether an individual's income exceeds 50K per year or not. And the following is a fairness property defined based on protected feature gender. As we can see here, the difference in the probability of predicting one for males and females should be no more than 10%. Then we say the neural network is fair. Next, we define our fairness verification problem. Let N be a neural network, Phi be an independence-based fairness property. The fairness verification problem is to verify whether N satisfies Phi or not. Here, our aim is to design an approach which allows us to show the evidence that a neural network satisfies fairness if it is the case. Otherwise, provide insights on why fairness is not satisfied and how fairness can be potentially achieved. And thirdly, provide a way of improving the fairness of the neural network. Next, we present the details of our approach. An overview of our framework is shown in Figure 1. Firstly, we learn a Markov chain D that models the behavior of given neural network N. Secondly, we will apply probabilistic model checking to verify fairness property Phi on D. And thirdly, if the probability is satisfied, we should return the result as verified and D as an evidence. Otherwise, we will conduct sensitivity analysis on all other features and hidden neurons, aiming to obtain the information on why fairness is violated. And lastly, we will optimize the neuron parameters based on the sensitivity analysis results, aiming to improve fairness. Let's look at the details of each step. This approach relies on learning a Markov chain that approximates the neural network. Why DTMC? The reasons are as follows. Firstly, a Markov chain allows us to perform analysis on unbounded behaviors. In the case of recurrent neural network, a cyclic Markov chain will be constructed for analysis, while this kind of unbounded behavior is known to be beyond the statistical model checking. Secondly, the learned Markov chain enables us to perform future analysis, such as sensitivity analysis, which are challenging for statistical methods. Lastly, as mentioned above, if the fairness is verified, the learned Markov chain will be provided as a human interpretable evidence on why fairness is verified. Here we also provide a definition of the DTMC. And as we can see here, to learn the DTMC, we must determine what are the states S and its initial distribution I, as well as the transition probability matrix A. Next, how do we learn a DTMC from a given neural network? Here we need to answer 3 questions. The first question is, what are the states to be included in S? As we aim to verify fairness, we must include protected features, prediction outcome, and in terms of sensitivity and analysis, we need to further include other features and hidden neurons. Next question is, how do we identify the transition probability matrix? We repeatedly sample inputs and then monitor the trace of the inputs. And after sampling a sufficiently large number of inputs, the transition probability matrix then can be estimated based on the frequency of transitions between states in traces. Next question is, how to ensure N is estimated accurately by D? Firstly, we would like to sample traces until the observed transition probability AW is close to the real transition probability A, which is shown in equation 3, where the summation of the transition probability difference is limited by the epsilon and the delta, where epsilon is the accuracy and the delta is the confidence level. Recent work 10 shows that if we sample enough traces such that for each state NP is greater than Hn, where NP is the number of transitions starting from state P. In this case, for any CTL property, the probability difference of A satisfying the C and AW satisfying C is bounded by epsilon and delta. Hence, if Hn is the bound on the number of the traces, then we must sample in order to guarantee that the learned DTMC is PAC correct with respect to any CTL property. This is our running example. For the network trained on census income, by setting the accuracy epsilon to 0.05 and the confidence to 0.05, 2.85K traces are generated to learn the DTMC, and the DTMC is shown on figure 2. The next step is to apply probabilistic model checking to verify fairness property phi. Note that phi is not a CTL property, but computing the probability of getting a favorable prediction when the protected feature is Fi can be reduced to a probabilistic reachability checking problem, which is then a CTL property. Hence, we choose to compute each probability term separately. For fairness property phi, we would like to ensure that the error of the probability difference estimation is bounded by mu epsilon and mu delta. Then how do we determine Hn? From our theorem 2, we can derive the epsilon and delta to be used in equation 5 to calculate Hn as shown here. Thus, we sample the model until NP is greater than Hn for all the states and compute each probability term, and then compare the maximum difference with the fairness criteria C. This is our running example. The probability of predicting 1 for females is 0.8483, and the probability for male is 0.8796, and the difference is then 0.0313. If we set the fairness criteria to be 0.1, then N satisfies fairness property. Next step is sensitivity analysis. In the case that the fairness property is not satisfied, we need to do sensitivity analysis on all other features and hidden neurons to identify who is the most responsible for violating the fairness. Let I be a non-protected feature or an internal neuron. We calculate the sensitivity of I as shown in equation 6. This is the sensitivity of I is the summation of the sensitivity of every state II, then the result is multiplied with the probability of reaching II from state I0 and the probability of reaching output L from II. Our approach analyzes all non-protected features and hidden neurons and identify the most sensitive ones for improving fairness in next step. In this step, we adjust the neuron weights of the most sensitive neurons aiming to improve fairness. we adopt PSO for finding new ways of the identified neurons, and its fitness function is shown here. Probability difference represents the maximum probability difference of getting a desirable outcome among all different values of the sensitive feature. And the accuracy is the accuracy of the repaired network, and the constant parameter alpha determines the importance of the accuracy over probability difference. Intuitively, the objective is to satisfy fairness and not to sacrifice accuracy too much. Thus, PSO will find better ways of identifying neurons and return a repaired network. Next, let's continue with our experiment. We evaluate our approach based on multiple neural networks trained on benchmark datasets, census income, which predict whether an individual's income exceeds 50K per year or not, German credit dataset, which predict whether a person's credit is good or not, bank marketing dataset, which predict whether the client will subscribe a term deposit or not. Jigsaw dataset consists of 313K text comments and is classified into 6 categories of toxicity. We trained 3 feed-forward neural networks and 1 RNN LSTM network as shown in this table, and the protected features are listed down here. We have race, gender, age, and religion. Next, we evaluate our method and answer multiple research questions. The first one is our approach able to verify fairness? Here, we perform fairness verification on all the 4 models, and the results is shown in the table. Based on the results here, the model on German credit with respect to age fails fairness criteria, and the probability difference is as high as 16.83%. And another model trained on Jigsaw dataset shows minor concern with respect to feature religion. Next, how efficient is our approach? We answer the question using 2 measurements. The first measurement is the execution time. As shown in this table, for feed-forward neural network, the average time taken is 4.25 seconds. For LSTM network, the time is around 30 minutes. This is due to the synonyms searching when sampling, and also not all sample contain sensitive word, results in more traces needed. The second measure is the number of traces that we are required to sample. This is often based on the number of category values defined for protected feature, number of predictions, as well as the probability distribution of each state in the model. The number of traces often vary between models and the protected features, and also as shown by our experimental results, the number of traces ranging from 2K to 35K. Although the number of traces is expected to increase for more complicated models, we believe that this is not a limiting factor since the sampling of the traces can be easily paralleled. Next question is our approach able to improve fairness? Here we conduct sensitivity analysis and optimize the weight of the neurons identified in the sensitivity analysis for the 3 cases highlighted here. And the results is shown in the table on the right. As we can see from the results, it shows the maximum probability difference before and after, and also the accuracy drop of the repaired model. We observe that in all 3 cases, we are able to improve the fairness while maintaining the accuracy at a high level. Next question is, how does our approach compare with existing approaches? The most relevant tools we identified are FairSquare and Verify. We evaluate the approach against these 2 tools on all 8 scenarios. For FairSquare and Verify, we follow the setting of independent feature distribution and check for demographic parity. For both tools, we set C equals to 0.15 as suggested and keep other parameters as default. As both FairSquare and Verify are designed to compare 2 groups of subpopulations, for those protected features that have more than 2 categories, we perform binding to form 2 groups. For the 6 FFN models, we set timeout value to be 900 seconds following the setting in Verify. The result is shown in this table. FairSquare is not able to scale for large neural network, and for all feed-forward models, it fails to verify in time. Both Verify and our approach successfully verified all 6 feed-forward neural network models, but our approach completes the verification within 1 second for all models, but Verify takes 62 times more time. For RNN models trained on Jigsaw dataset, FairSquare cannot verify because it supports loop-free models only. Verify supports RNN, however, it does not support text classifier. In conclusion, in this work, we propose an approach to formally verify neural networks against the fairness properties. Our work relies on an approach for learning DTMC from given neural network with PAC correct guarantee. Our approach further performs sensitivity analysis on the neural network if it fails the fairness property and provides useful information on why the network is unfair. This result is then used as a guideline to adjust network parameters to achieve fairness. We implemented our approach on top of SOC rate, and it is open source. Comparing with existing methods evaluating neural network fairness, our approach has significantly better performance in terms of efficiency as well as effectiveness. That's the end of my presentation. Thank you.
Okay, I will stop sharing the screen now.
Well, thank you very much. Thank you,
Okay.
Ping Sun. I think
Thank you.
this worked quite well. So, I mean, it was very fast, but I could follow. So I posed a question in the chat, and I would encourage the audience to also ask questions there. The next talk,